Hey all, so we're going to be looking at proof infinite sets have equal cardinality. So we're going back into things with proofs now that we've gone through functions, and we're actually going to use a lot of those functions notes to start using these methods of proofs. So review those notes as you need to, especially proving injectivity and surjectivity. But for now, we're going to get started in chapter 14.1, two problem sets. Get yourself ready for notes, and we're going to begin. So, infinite sets are sets with infinite elements. So, we can also say infinite cardinality. Now, this is already an idea that you're really familiar with. Examples are most sets of numbers. So, the natural numbers would be infinite. The integers, real numbers, any interval of the real numbers, etc., are all going to be infinite sets. Now, when we say that infinite sets have equal cardinality, what that means is that two sets have equal cardinality when you can write a bijection between them. So this is where the idea of this ties in. And so infinite sets, like for example, we've got the natural numbers 1, 2, 3, 4, 5, etc. And the real numbers, they're both infinite. But what's actually really fascinating is that they are not the same cardinality. They don't have the same number of elements. The real numbers, as you maybe would imagine, is that they are much larger than the natural numbers, even though they're both infinite. However, there are plenty of infinite sets that are. So if you look here in number 2, it says show that the natural number cardinality is equal to the integers. So some infinite sets are equal and some aren't. So we'll talk about using this bijection idea to prove different cardinalities are equal. So show that the interval of 0 to 5 and 0 to 10 have the same cardinality by describing a bijection between them. So with all these types of problems, you want to start by try to write a bijection. Now, in this case, we want to look at the sets that we're interested in. So I want to write from 0, 5 to 0, 10. And I want to write a bijection in there. And since we can identify our sets, we're like, oh, well, this is the interval 0, 5 to 0, 10, twice as big. I'm going to say f of x is equal to 2x. Now, our second step is that we have to prove this is a bijection. So write one, and then you just want to test for injectivity and surjectivity. And, we want to make sure that we're testing for both to prove that it is a bijection. So I'll test for injectivity first. And remember, for that, we say that f of x is equal to f of y, and we want to show that x is equal to y, 2x is equal to 2y in this case, x equals y. Excellent. For our surjectivity, we want to say that x is in the codomain, so x is in 0 to 10, like so. Well, we know that, I'm actually going to change that to y so that our notation's a little bit easier. So then we want to show that f of x is equal to y for some x in 0, 5. Our function is 2x. So then x is equal to 1/2 y, which would absolutely be in the interval 0 to 10, all divided by 2, which is 0 to 5. So now that we've shown that a bijection exists between the intervals 0, 5 and 0, 10, we can now say that the cardinality of 0, 5 is equal to the cardinality of 0, 10. And we end our proof, little box. Now, oftentimes the bijection will be a little bit harder to write than this. So we're going to go through a couple of famous examples of bijection so that you see those. And also you can use these as stepping stones. And I'll show you what I mean by that in a couple of minutes. So one of the most famous ideas of proving infinite sets are equal is this idea that the natural numbers has the same cardinality as the integers, even though our intuition says, oh, well, shouldn't the integers be twice as big because they have all those negatives? Now, a way to write a bijection if you're not sure is I like to start out with thinking about how would I assign elements in terms of ordered pairs. So if I have my natural numbers and my integers, my natural numbers are going to be 1, 2, 3, 4, 5, 6, 7, etc. And with my integers, I have both my positives and negatives. So maybe I want to make sure that I am not starting and writing 1, 2, 3, 4, 5 all the way down just like that, because that forgets 0 and that forgets our negatives. So I'm going to start with 0. After that, I might say 1, and I don't want to go to 2 next because then I'm losing my negatives. So I would then say, okay, well, next will be -1. Then 2, -2, 3, -3, and so on. And I can say, oh, okay, well, this is maybe not a traditional function that we would write like we saw in this problem of 2x, but there is a pattern here based on whether or not the natural number is odd or if it's even. So that's how I'm going to write a piecewise bijection. F of x, I'll say that it's 0 where x is equal to 1. If x is even, so 2, 4, 6, you'll notice 2 goes to 1, 4 goes to 2, 6 goes to 3. So this would be 1/2 x when x is in the even numbers. And when it's in the odd numbers, I'm going to say that it's 1/2, and then I want it to be negative. And since we start, if I just did 1/2 negative, that wouldn't work out. So I'm going to say 1 minus x for the odds. And just, I can check that out. Say, all right, 3 is equal to, would become -3, 1 minus 3, which is -2, 1/2, perfect. Carries on like so. I then am going to do a quick check to see if that works out here. It works out there as well, so I can be more concise. Cancel that out, and my bijection becomes 1/2 x if x is even, and 1/2 1 minus x if x is odd. Now, to prove that it's a bijection is going to be straightforward. If you want to do that, I just want to keep the video from being 30 minutes long. Feel free to check that using the work that's available. Now, what we are going to show next is sort of a similar idea, but just with the real numbers. So showing that all the real numbers is the same as the positive real numbers. So all the real numbers is equal to the interval 0 to infinity. So when I write my bijection from the real numbers to 0 through infinity, the question here is what function can I have any x value in but only get positive y values? So I can go from negative to positive x values, but only positive y values. And the answer to that is exponential. This is why it's really helpful to think about all the different types of functions that we've seen. So if I identify, oh, exponential has that quality, I'm going to say that f of x is equal to e to the x. Now I want to show that it's injective. So if f of x is equal to f of y, e to the x is equal to e to the y, so x must equal y because e to the x is 1 to 1. We've seen this. Now, surjective, we want to say some y is equal to f of x, and that value is ln of y is equal to x. Now the domain of ln of y here, the domain of that function is 0 to infinity, which is what we're given as the range of f. So that's equal to the range of our function. So that means that absolutely it is surjective. Hence, since a bijection exists, their cardinalities must be equal. So again, it's one of the cases of writing your own function. Here, show that the positive numbers have the same cardinality as just the interval of 0 to 1. And so this question again becomes, if I want to write an equation where all the numbers are there for the x values, but only from 0 to 1 on the y values. Oops, shouldn't have colored in that. Nice open bound. That's important. I'm going to ask myself, in terms of thinking about the graph, I want to have a value that goes in for this whole domain here, but only crosses through here down, like so. Now, looking back at my knowledge of graphs, I'm going to say, oh, well, that looks like e to the negative x. And it does. And this could be any base. We're used to using e, but you could have used 2. You could have used any of those values. And if I plug in, so if I plug in any of our positive numbers here, I'm going to get out a negative like so. You can show that this is a bijection exactly the same way as we showed in number 3. So what we know then is that the cardinality of the positive real numbers is equal to the cardinality of the interval of just 0 to 1. Now here's what I mean by using the supports from previously, is that with all these cardinality rules, if you've written a bijection, the transitive property still holds. So what that means is that we have just shown that the real numbers have the same cardinality as the interval 0 to infinity from number 3, and the interval from 0 to infinity has the same cardinality as the interval from 0 to 1, and that's what we just showed here in number 4. Therefore, the cardinality of the real number, so all the real numbers together, is equal to the cardinality of the interval from just 0 to 1. This may seem like something that does not feel true, that all the real numbers, the whole number line, is the same as this little interval in here. But using our knowledge of bijections and our understanding of the transitive properties, we hold that this must be true. If you have questions about anything you've seen here, I will be available through office hours, by email, or in the comments. Talk to you later.